Good afternoon, ladies and gentlemen. Welcome to TechGig webinar series, our endeavor to impart techies. We believe that sharing of knowledge is the key to enhance our skills and grow us as professionals. With this principle in mind, we have initiated a series of webinars conducted by industry experts to give you all a crisp insight of various domains. The topic of today's session is practices and patterns for building scalable systems. Our guest speaker today is Mr. Balaji Rajagopalan, member of Technical Staff 2, Software Engineer at eBay Inc. Balaji has 12 plus years of experience in development cycle, including system requirements collection, architecture, analysis, design, development, maintenance, enhancement, and product support. In his previous role, he worked in the bioinformatics space, including startups for 5 plus years. Currently, he is a solution architect in eBay Inc., influencing long-term architecture and technology stack for PayPal settlement systems. In his spare time, he likes to tinker with open source contributions and is an avid Android enthusiast with a couple of published apps in the Android market. So without further delay, I introduce you all to our guest speaker. Over to you, Mr. Balaji.
Thank you. Can you guys see my screen? Okay, so the agenda for today's webinar is scalability and practices for scalability. We'll just go through what we mean by scalability, the definition of scalability. We'll look at consistency versus availability. These are some of the key factors that you decide when you build scalable systems. We will look at something called base. We'll look in detail what base stands for. It's basically available, scalable, and eventually consistent. And then we look at certain practices for scalability. Most of these practices that we are going to talk about, or some of these definitions, are pretty much common across the industry. Some of it might be new to you, some of it might be you do it, but you don't know what the name is. It's like software patterns. Many of us do factory patterns without knowing it's called factory. So we'll go through some of the practices that we do across the industry, some of the common practices that are available in the literature as well. And then I'll definitely take questions and try to answer them as much as I can. First is definition of scalability. So what do you mean by scalability? Like, whenever somebody gives you a requirement, nobody calls out the scalability portion of it. It falls under what we call as a non-functional requirement. Nobody says your operation, when a product manager comes and meets the engineering team, nobody comes out and says your SLA should be 50 milliseconds. So most of scalability is abstracted into what we call as non-functional requirement. So when you say your systems are more scalable, at least what my definition of scalability is, you maintain your current SLA. So if your current SLA is, say, 30 millisecond or 50 millisecond, in spite of if you're taking, say, 100,000 web requests at a given point of time, and then now you scale it to, say, 500K web requests, your SLA should not deteriorate. If it's 50 millisecond, it continues to be in 50 millisecond. And also the fact you have to maintain SLA even if you add more features to it. For example, if your Pay API takes, say, 50 milliseconds for 500K requests at a given point of time, even if you add incentives, promo codes, etc., your SLA still maintains the same 50 milliseconds. And the reason for that is systems that are downstream, upstream, that are kind of interacting with your peer services, expect that level of SLA from you. Once you establish it, these things are very hard to change, unless you're kind of improving your performance. Like if you're going down, people are happy, but most of the times, if you try to go up, there'll be a lot of resistance. And one that goes without saying is if you're adding more nodes to the system has to scale. So it's like you definitely should see an increase in performance by adding more nodes. It need not be linear. I mean, it's very difficult to get a linear increase, but ideally you want to have that. And then your system should be able to handle heterogeneity. What we mean by that is, for example, if you have a system upgrade, like you have a kernel upgrade from 2.4 to 2.8, or your machine memory goes from 8 to 16, whatever, 64 GB, whatever be the case, right? You don't have to rebuild your servers just to run on that particular type of hardware. Ideally, your system, your services should be independent of hardware. So in case even if operations tomorrow decides to build something different completely, your software should be able to handle it. And the other thing is your services have to be, have to take on failures. I mean, failure is a given. Systems will fail. That's the fundamental tenet. It's a question of how you manage your failure cases. That's where scalability comes in. And of course, all this, when you're adding more nodes, doesn't mean it increases your operation cost. So any scalability solution, if it involves a lot of operational expense, I mean, orgs can still do it, but that's not an effective scalability solution. So that's what we mean by scalable systems broadly. So on this slide, I'm going to talk about the CAP theorem and what it means. So there is this programming paradigm of ACID that we see in atomicity, consistency, isolation, durability. ACID gives us a very clear and a very, it's a classic clear computing paradigm, right? So if your database is up and running, you commit. If something is wrong, you just go back and say, okay, I can't do it. You write something to a data store and you immediately read it, you get the data back. So the consistency is really strong in a traditional ACID-based system. Whereas the CAP theorem, what it says is, if you have a distributed system, it's impossible for you to guarantee all three. You cannot get strong consistency. The system will not be available all the time, and the system will not be able to do partition tolerance. What we mean by partition tolerance is like anything that grows across the network, right? So unless you're running everything out of a single box, things you need to have network across in your system. So partition tolerance is something that's given. So what the CAP theorem says in short is you either get consistency or availability, and you have to pick one over the other. So traditionally systems, like if you look at any web system, right, making this choice is very important. So for example, if the user is going through a checkout and then is trying to do add an item to his cart, your database is down for whatever reason, you are either going to go back to the user and say, I cannot take this right at this point. So it's a bad user experience. Or you go back and take the card from the user, but you don't persist it immediately, right? So your system in that sense is highly available. If at the same time, if for example an inventory system that's trying to read the number of orders that you have got so far is not going to get that data. So it's highly available, but it's not really consistent. So it's always you have to pick one or the other. So either you can go back to the user and say, I cannot take your addition of this item to your cart at this point. Or you take it, but then certain other systems will not know that you have actually taken this, as certain systems downstream, like for example your inventory system, your billing system, will not know that you have actually taken this item into the user's cart. This need not happen all the time. So it's something you have to understand. So what CAP doesn't necessarily mean you will get only consistency or availability. What CAP tells you is when system starts to fail, you can either, your system has to take either the consistency approach or the availability approach. So most web systems will try to go on the path of being consistent. So when we say consistent, we'll take the path of highly available and choose a path of what we call as eventually consistent. When we say eventually consistent, it doesn't mean like it will happen day after tomorrow or like 2 days from now or etc. Eventually, consistent system, the order of consistency is sometimes like seconds or milliseconds or maybe minutes. Classic use case would be something like you go to your Facebook page and then you say like on something, right? And then your friend logs in, he may not actually see that you have given a like on a particular post. But if he logs in a couple of hours later or even like 2 or 3 minutes later, they'll see the like. So it's like but you as a user actually saw that like, but your friends need not, when they log in, need not immediately see that like. So it's an experience that you have to live with. So whatever you decide, either when you decide to go with a highly available system, it drives the user experience as well. It's just not like a technical decision, it's a product experience as well. So the SCAP theorem was proposed by Eric Brewer during he was with Dichotomy, which was eventually brought out by Yahoo. So this it's called a theorem because a bunch of academics actually proved you can either get strong consistency or you get availability. So you have to either pick one or the other. So what it means is in today's system, you just cannot afford to do any kind of distributed transaction. So any application that tries to do distributed transaction is bound to slow the system, and it's bound to have a bad user experience, or it just will not scale. It just will fail. And the reason is this, right? So you need to have distributed databases because if something goes down, you're not taking the whole log down. For example, if your say your inventory database goes down, your ability to take the cart item should still be there. But hopefully the inventory system comes back up at a point later in time. But because of that, you're not giving a bad user experience. You're still able to take cart rights. So distributed databases is a fact of life. So if you're building high quality, lot of traffic production system, you cannot put everything in a single database. So distributed database is a reality and it's needed. But if you try to do a distributed transaction, that's when things get really slow down. So if you're trying to do if you're trying to lock tables across rows in tables that are in different databases, your system will bound to be really slow. Like any protocol that does it today, like two-phase commit or Paxos or quorum protocols. There are a lot of protocols in the literature. And these tend to work like if you are a 4-node, 5-node system. But if you scale it beyond like say 50 to 100 nodes, there is a lot of chatter between like even for the coordinator to come in and fix which protocol, which one gets to commit first, etc., etc. So you tend to slow your system really down. So your SLAs are way off. So when you try to do atomic transactions, all the transactions should be local. There is no concept of a distributed. You should try to take distributed transactions and abstract it in a different sense. So either you queue it or you invoke an operation or something that, depending on your flow, depending on the workflow, depending on where you are within that particular workflow, you have to accommodate distributed transactions, but not in a straightforward way by locking rows across databases. So what this CAP theorem eventually implies, especially when you're building a web-based system, is what we call something called base. This is not a very clear classic programming paradigm, but this is where the systems tend to be today. What base literally stands for is your base. The system is basically available. It's scalable, and it's eventually consistent. So you give up certain constraints of what we call a strong consistency. If you're going to write, if you take a user's, if a user goes through checkout and adds a bunch of items, the subsystems that depend on this are not going to get the data read immediately. They will eventually get it, but they're not going to get it immediately. That's the difference in paradigm. And when you're going with this paradigm, you have to build a lot of components, a lot of abstractions to achieve this type of paradigm. But it's not something new. It's kind of it's well known. Even like a DNS is a classic example. If you come up with a new website now, somebody that's logging in, say 500,000 kilometers, like 5,000 miles away from here, is not going to get that site immediately. So, but eventually, you know, the DNS picks it up, the ISPs pick it up, and eventually they're able to come to your site. So it's eventual consistency is kind of a way of life, but you just have to see it see it a different viewpoint, and it's been done before. It happens across us. Like even when you're loading a file, the user doesn't expect the user doesn't expect the image to be seen across everywhere, but they do expect like an experience where, like JavaScript, right? Like you show something to the user that something is happening, but it's still eventually consistent. I mean, eventually it'll get there. So one of the fundamental criteria that you have to understand before trying to take any kind of scaling approach is you need to understand your own system. So if you're not able to do any kind of distributed transaction, any kind of uncertainty that you have to build is all managed within the application. So you have to understand how your existing system behaves. So for example, if you have a system where you have 100K users, and then you want to scale it to 500K users, you try to simulate your existing system with data that you know. So if your most common use case is a sign-up use case, 80-20 rule applies. So 80% is a common user sign up and 20% is guest or whatever. So you try to go with your most common use case and try to see if your data models, your data validations, your service interactions really scale appropriately. So if you say you're doing 100K user signups and then you're doing 200K transactions at that point, if you scale that out to 500K, you should see a linear increase to 1 million writes to the database. When you do this type of dissection, sometimes you figure out that you're just doing 800K, or on the contrary, you are doing 1.5 million writes to the database when you should be doing 1 million writes. And what traditionally happens is it's probably a bug in the system, or you figure out somebody is actually doing a better job. Some component is actually doing a better job than what you expect it to be. So this is something what is called a data causality map. You have to build your system. You have to understand what your current systems are before you kind of go out and say, okay, scaling a system is not difficult. We'll just find a cloud provider and then we'll get more web servers, more app servers, and then you're done. It just doesn't work like that. So if your database is your bottleneck, the more you actually scale, it'll actually bring the system down faster. So everything works fine if you're taking to 1 million, and then it works fine till 2 million. But then all of a sudden, when the next customer logs in, he or she brings the whole system down, and it impacts all the current users, the 2 million new users who are using the system. So it's very critical that you have a clear understanding of your existing system. So scaling is just not by running more VMs. It's about your application architecture, your data architecture, the product experience. A classic example is the Facebook like, right? So if you like it, but you say like, but your friends don't see it immediately, which is fine, and you can live with it. And also the cost. So you have to figure out if you want to eventually scale a system, whether it's really worth spending that much time and money onto it, or you can live with the experience. So even an asset experience is fine for certain parts of the system, right? So for example, if you're doing a reporting application and it goes down, it's fine. I mean, you don't have to really break your head on it. But if it's a customer-facing experience, you don't want to have a bad customer experience. So it's very critical you understand your existing system. Where any cloud provider or any VM stack really helps you is ability to actually validate your current understanding. So if you have difficulty today to scale, to even mimic this type of request, today you can easily go to any cloud provider and increase your VMs and test all this out. So so you should be able to leverage existing utilities to understand your system better. The tricky portion of this is keeping that understanding throughout the life cycle of the organization, right? So today I come up and I come up with the data causality map for the subsystem. And it's very difficult to maintain that map throughout, because things move on, orgs change, etc., etc. People move, so it's very difficult to maintain that. That's the reason not many folks continue to do this throughout the life cycle. Another thing you have to realize is not all data is equal. So this is a critical assumption. So data as it flows through, everybody traditionally has a workflow, right? So user goes through checkout. So there is the user service invocation. There is the orchestration layer that comes in. There is the item, the cart writer, and then there is the inventory, then billing, etc. Right? So, but the same data, transactional data, if you have transactional data that's going through a pay flow, it's not, the user data at that point is not that critical as the transactional data. Like for example, if you want to know the user profile, but for somebody who's going through a pay API call, the user profile data is completely irrelevant. So at that point, it's a transactional data. The user profile data is a good thing to have, but your guarantee to the system is purely on the transactional data. Same thing on the user profile page, right? So if a user comes in and even on PayPal, if they want to see their bank account, their credit card numbers, and all their previous history of transaction, etc. If you show them the credit card, bank account, and then if you're not able to show the transactional history data fully, that's fine. So it's like you have to figure out what data is needed in what flow, and build your services around that. So it's not like a single shot solution for everything. It depends on the workflow that you are in. And also, this is something not many engineers tend to focus on. You have to figure out what is your data retention policy as it applies to your org, etc. The reason for that is you want all your SOR, the system of truth record, to be probably in a good database like Oracle or MySQL or any kind of relational database, right? That gives you strong asset properties. But then the SLA around those data is what drives every behavior, right? So if, for example, users are a lot more interested in 2 months of data traditionally compared to 2 to 24 months, and for example, and my interest in any data that's greater than 22 years is really less. So maybe for compliance you have to hold some data, but that doesn't mean that have to be in your current system. I mean, the SLAs are different. So even if an auditing body is going to come to your org, you don't have to like give them like within 50 milliseconds 7 years of data. That's not the expectation, right? So, but within 50 milliseconds, you have to try, for a user who's going through a transaction flow, you have to satisfy the pay API. So you have to figure out like what type of data you're doing, what type of data retention you have, and how you build your SLAs around it. And this impacts because anytime you spin a disk or anytime, even to read, and then when you're spinning disk to write, your SLAs are way off. So you have to understand how data comes around your SLA. So you have to do this kind of homeworks to, you have to do all this type of homework to set the SLAs in the first place. So some of these things you don't even need anything. Like all you have to do is to trim the data around, and then you're good to go. Your SLAs that were like, like 300 millisecond comes down to 100 millisecond just because when you're writing your indexing and then the index is building, the size of the table is so large, the index tends to be large as well. But the moment you start trimming it, things tend to be faster. So understanding these type of requirement actually drives a lot of factors around your SLA, the data, the way you want to replicate data, whether you want to normalize or denormalize data for that particular use case. All this is driven by your existing behavior and also the understanding that all data is not equal. So if you're normalizing and then you're joining like 8 tables together to do a write, you're probably hosted. So at that point, you have to figure out how to denormalize your data, do one write someplace, but then eventually when it goes to your system of record, it's very consistent. And of course, there are techniques that you can do, like partition of your data, sharding of data. I mean, they do have their own advantages and disadvantages. So like user profile data, you can probably shard it, and then based on the user account number, if you have 10 shards, so probably based on the user account number, you go to a model of 10 and then go to shard 1 or shard 2 or shard 3, whatever. Right? So there are techniques of data sharding, and people do apply this at a wide level as well. So if you are a Facebook user, you probably have friends who are probably a lot more closer in your geography compared to somebody across geography, right? So you can use those kind of techniques as well. So if I'm out of Chennai, there's a good chance most of my network is out of Chennai. If you're out of Delhi, most of your network is out of Delhi, and then there are a couple of users who probably are not out of Delhi. So if you're trying to do a data center for such type of applications, you probably try to say, okay, just to minimize round trip, these type of users go into the Delhi data center compared to these kind of users who go into another geography data center. But then you still have to do a certain amount of golden gating, replication of data, etc. But then your core customer experience is not compromised because your reads tends to be faster. Most of my friends are probably within my area, so when you're building the graph, it's a lot easier to build that graph also. So it just any type of example you can take it and drive the user experience around it. So now we come down to some of the core principles of scaling a general system. So the first principle that we traditionally apply is what we call partition by function. So if you are an SOA enthusiast, you probably know what I'm talking about. I mean, this is not something new. It's even when you build a single monolithic code, you try to make it more modular. But with systems that are a lot more decoupled, you try to build sub-services or subsystems that you can scale independently. So any system, I mean, most of the system by design should be loosely coupled. Any tight coupling will introduce dependencies that you might find it very difficult to walk away from it. So you have to be very careful when you build your systems that they tend to be loosely coupled. And I mean, this is something, it's kind of an irony as well, but this is kind of a tight line to walk, right? So you are actually breaking a huge monolithic system into multiple subsystems that you can scale up individually. But then managing the interaction becomes a little bit tricky, and then you have to build a lot of software abstractions around it. So, I mean, if checkout is just one huge monolithic app, yeah, it's great, all complexities within it, but you'll just not be able to scale, you'll just not be able to honor that number of checkouts that you do today in a cost-effective fashion. But then you start saying, okay, this will be the user service, this will be the inventory service, that will be the orchestration layer, this will be the billing service. Yes, there is a lot of interaction that happens between these services. So you push the complexity a little bit into the interaction, how these systems interact. So you give up on the simplicity of being a monolithic app, but then you can scale in individual subsystems, right? So for example, if you are a fulfillment system and then or a settlement system and then the pay system, on the pay system you can be very elastic during the day, and then your settlement systems can be a lot more elastic during the night. So that's when you settle a lot of transactions. So it's like you can scale the settlement system separately. You can add more nodes, or make it more elastic during the night, or bring down the elasticity of those services during the day, right? But then your transaction services are up and running, picking up during the day. But you need that kind of partition. Otherwise, you have to scale the monolithic app, and it won't be cost effective. So partition by function, whatever you call it, function decomposition, SOA, we do it at the code level all the time, jars, packages, bundles, etc. But that's a guiding principle that you have to follow. And there is nothing like a single solution to all this. You figure out as you go through. So if you're trying to do too much in a service, yeah, you probably are very coarse. You probably have to change the granularity of your service. Uh, or if you're just doing too little, also you have to figure out, is it like really worth being a service or not? Whether can I live with a static library? So all this you have to make a call, and there's nothing like a formula to all this. Sometimes you just have to go through real pain of going through production systems, get your ass kicked, and then you realize, okay, maybe I was doing too much on that. It needs to be separated out. The other thing that you have to be aware of is just because the JVM supports a lot of threading, etc., you shouldn't be like initiating a lot of threads per request. And the reason is, any thread. I mean, if you're doing a lot of IOs for a queue per request, it also takes up the socket space. It takes network, etc. So most of your app tier is probably doing a lot of this logic and opening a lot of socket connections. So if you're trying to do a lot of parallel threads, it consumes the system resources. So in a sense, you are blocking other requests from being done within the SLA. Same thing on concurrency as well. So you need to make a call. Like there should be parallelism because otherwise it's very difficult for you to maintain your SLA. But that doesn't mean you just start killing other requests or consuming so much that other requests are not able to be placed on that particular node. Same thing on concurrency, right? So if you're trying to do too much of like when your subsystem is trying to talk to the transaction system or the settlement system and the invoice system, etc., and you need data from all that, you should probably look at your system. Is that the right data model? Why am I doing so much low-level locking? And that too across so many domains that probably should not be talking to each other, right? So when you're doing concurrency, it's good to have a concurrent paradigm, but it comes with a grain of salt. So you have to, again, there is nothing like a silver bullet to all this, right? So there's no single formula. You have to go through, you have to look at your system, you have to look at the SLAs, and then what you're doing, try to figure out what the best approach is. And what goes without saying in all this is, decentralized. There should not be a single point of failure. So even when it comes to development, right? So there should not be a single point of failure. So anything that you think will take the whole system down will make the system basically not available. You should walk away from it. So you should figure out what's the best way to decentralize. So on the next thing is everything is local. So all state that you know is local. So a given system can talk to multiple subsystems, or is talking to multiple systems upstream, downstream, or in a parallel fashion. But all your data, all your state data is local. So if I'm building an inventory system, it's like I should not be depending on the cart system being available all the time. So if it's available, good and great. So because if a user is adding an item to the cart, okay, as an inventory system, yes, I need to know that so that I can place an order with my vendor to get that cart into my warehouse, right? Or if I'm a settlement system, yes, so if I know if a particular transaction is going through now, I can settle it quickly. But I shouldn't be worried about if the transaction system goes down, that's fine. So I should still be able to do settlement for transactions that I know of. So if you are in the business of trying to figure out what is the state of this particular entity is in a different system, it leads to a lot of chattiness and systems will be down. So it's like you are not able to do your work because somebody else is down. So all state is local. So you have to make sure this you don't do a lot of trying to figure out your business logic based on somebody else's state. Whatever business logic you do, whatever logic you do, is purely on the state that you know of as it is. You are the system of truth. And you should have the ability to handle failures locally. So systems, as I said, other subsystems might be down. For example, if a user buys, if a user buys a diaper, a user buys a baby toy, there's a good chance the user is going to buy some other baby-oriented material. and you want to publish that to, say, the recommendation engine or the user recommendation engine, right? But that system could be down. So that doesn't mean you don't fulfill your duty of fulfilling that particular transaction. You probably do an internal queue or separate wait for that system to come back up. But you go through your action as if it's like you're blind for like the horse in the race, right? So you just go through in your track, and then act as if systems will come back up again and they will figure out a way to get the data. So what we call, this is an interesting paradigm, what we call separate promise from action paradigm. So even if you know your own database is down, like if your system of record is down, but you still end up getting a request, you try to go through the request. You see, okay, the request is good to go, but unfortunately my database is down. But I'm still going to cache this. So I'm going to put it in a, some kind of mem cache or whatever internal caches you have. You try to put that in and say, okay, or you have an abstracted internal queue, so that you still are to an interacting client, you are still up and running. But then internally, you actually know, okay, I can do this only for a while. It depends on my cache capacity, etc. But then you can still go on, like you can still take 20 gig of requests because you have internal caching for 20 gig. And you hope by the time your database is up and running where you can dump this 20 gig and then you're done, right? So there are ways to build these type of abstractions out where even when your system of record is down, you can still act as if everything is good. Eventually, that is. And the other thing that when you go through, this is kind of tied to a couple of previous slides. So what you realize is your caching. It depends on what type of caching you do, but you have to figure out anything that gives you a better hit rate, right? So if that means you're choosing one stack versus another stack, etc., one mem cache versus something else, you have to make the call. But then whatever, you need to have good caching, so that your cache ratio is high, and also you don't cache high velocity write change data. I mean that's not going to work anyway. So when you cache, you just have to make sure it's mostly read only. It kind of goes without saying, but then when you do your system breakdown, you realize you do some of these things that are kind of fundamental, but then it kind of falls through the cracks. So it's very important that you have proper caching in place, proper DB caching, or whatever cache that it's appropriate to your use case. Okay, and the next principle is idempotency and retries. So some operations, especially this must be very familiar for folks on the SOA world, some operations are naturally idempotent. Right? So any type of read operation, right? So it's naturally idempotent. I call you 20 times for the same read. Even if you fail to get a couple of my requests, that's fine. You can still read the data, give me back the same data as you read it the first time. But some operations are not, naturally idempotent. So, for example, if a user is going through PayPal system and then tries to pay, but then imagine you're going through a wireless network and then you're either through a cell phone or going through a train and then goes through a tunnel, etc., etc. So where the network characteristic is so bad, like we end up getting multiple requests, or your app thinks, okay, I haven't called pay, so I'm going to call pay again. So that doesn't mean you end up charging the credit card multiple times, right? So you have to make sure certain operations, and these operations are really tricky sometimes, but then they are very core to your business as well. So if somebody calls pay for the same use case, you should not charge their credit card multiple times or move money from their bank account multiple times. Same thing with the cart example. Like if somebody is saying, okay, buy this, the app may not figure out that it actually, you might have processed the request, but then you might end up getting the same request again. So you have to maintain some kind of state or some kind of unique characteristic to that message to make sure you are idempotent. And same thing applies to retries as well. So people might retry multiple times. And idempotency is something you just don't do it for your external folks as well. You have to make sure you do it for your internal folks as well. So, your internal clients, any client, right? So if they end up changing the state in a way that's, that's critical, you probably have to make sure your operations are idempotent. This has been a very hard learning for us. We did figure out for certain type of use cases, some pay operations were not idempotent, and it was really pain to go through some of these. So, I mean, these are something you may not even realize unless you run your system through production, right? When you're going through use cases that you don't run it on a QA system day in and day out. So it's probably like 80-20, so 10 to 15% of the use case you don't even think, but then they are like 100,000 of your use cases, right? So, so it's something you have to think through and make sure it's normal. It's not ingrained even with folks who are kind of very aware of certain SOA principles, that they do find it difficult to make sure idempotency and retries are built into the system. It comes at a cost, but then it makes the system behavior far more reliable. And the next practice I want to talk about is asynchronous scaling, is what we do. So most of the time I mean, if you're familiar with any kind of queuing protocol, JMS or internal queues, anything that you're doing proprietary within your own stack, anything that you can do in an asynchronous fashion, you do it. This is not a new paradigm either. Like even if you're doing a front-end web flow, right? So JavaScript is a classic example. Right? So Ajax is classic example. So you try to do as much as you can, depending on the user experience, the product experience, as much as you can in an asynchronous fashion. To send out an email, you should not be invoking an operation. Right? You can, but if it is through a queue, right? So it's through an internal queue, it's fine. So you try to keep your existing systems as trim as possible and try to move as much as you can to the asynchronous world. So you try to push as many messages as you can. So if you want to monitor the risk, if you want to monitor the recommendation engine on an e-commerce site, example being somebody who's buying baby items, they tend to buy more. You don't have to, immediately inform. It need not be a synchronous call to the recommendation engine. You can inform the recommendation engine, whatever they are running behind the scene, the risk engines behind the scene, through messages. But there is a caveat though. So I'll just go down to that as well. So some of the more popular one that open source compliant is AMQP. That's by the Apache community. So there are a couple of implementations: RapidMQ, OpenAMQ. So not all queues are identical. So if you look at the RapidMQ implementation versus OpenAMQ implementation, yeah, it meets the specifications, but there are certain what should I say, certain intricacies that you have to figure out. So so you have to know the system. So it's not like, yeah, I got a queuing system, I know this is what it's supposed to do. This is where kind of the road meets the rubber, right? So you have to understand, you cannot be hand-wavy beyond a certain point. You have to understand why you're choosing certain queuing protocols and what you get and what you don't get. So, and the reason is this. Traditionally, when you look at any classic e-commerce that's taking reasonable amount of traffic, or any system that's taking reasonable amount of traffic, you are firing a lot of messages. You probably are firing roughly, depending on an average, you're probably firing, 500K messages per minute easy, depending on what type of systems you're running. Sometimes 500K even per minute or per second, right? So asynchronous scaling cuts you in both ways. It's really good at scaling, but you have to get it right. So you have to make good choices. So it depends on a certain amount of experience that you want to have, whether it's persistent or non-persistent. A classic example that's always thrown around in terms of queuing is a stock quote, right? So if I'm interested in, say, stock of Google as of now. But then the stock, I mean, it keeps changing. So I get a message that's 400, say it's 400 rupees now, but then it moves to 450, and again it moves back to 475. For whatever reason, I didn't get the 450 quote, but then when I look at my app, I end up getting 475, which is fine because at that level, as for that particular application, you are fine with the most recent code. You don't need all the previous history of codes, right? So, so at that point, maybe you are fine with picking up a non-persistent queuing mechanism. But that will not work for, like, for example, when you're going through a user sign-up, right? So user sign-up means you have to inform risk of something. You have to send an email out to the user. Otherwise, it's a bad user experience. So in that way, it's not like, oh, you can drop a couple of messages here and there and you can move on. No, in certain use cases, you cannot afford to drop messages. So you have to figure out, you know, what type of a persistent queue you want to choose. And then when you're choosing persistent queues, it's like you have to figure out the retention window, whether you do like a 14-day retention window, 21-day retention window. What we mean by retention window is even if your subscriber goes down and the subscriber comes back up after X amount of time, the subscriber should be able to process that message. So even you're publishing something to some engine to send out an email and that engine is down, if it comes back up, it should be able to get that message back and then send that email out to the user. So for certain behaviors, you have to make certain choice of queues, and you have to be careful of what you choose. It's all driven by the product experience as well. And so most of the time, the other thing that you have to, if you have a subscriber, it's better that you, if you're building something that's taking huge amount of production traffic, you might end up getting messages that are the same, like, you know, that you might end up getting the same message again and again. And you should have the ability to figure out, okay, this message I've already processed and this one I haven't. So it will be great to have only once exact order messages, but it is really tricky to get those type of queuing protocols. They do come, but you have to make a lot of customizations. It's expensive to build that out. So as I said, because you're firing so many messages at a given time, you know, queuing protocols normally it's like, you know, there is no the implicit assumption is all messages are successful. Only, you know, unfailures is that case, right? So normally, when you're firing, say, 500K messages per minute, you don't want to realize that something is wrong after 2 or 3 hours. So you probably want to realize that something is wrong within, you know, minutes of what, you know, within minutes of something failing. So even when you go back to RapidMQ, what are the queues that you decide to use? Sometimes you might have to build custom clients. So the reason for that is, when you are going through non-persistent queuing, the message does not even, you know, there is a good chance the message has not even left the kernel stack or even the network stack, right? So it still hasn't even gone through the network interface card. But still, the software comes back and says, yeah, done, message published, right? You can live with that behavior, you know, for use cases like, you know, stock, etc., etc. But you have to make sure, like, you know, you get some kind of acknowledgement after you fire, say, 200K or 500K messages, that at least the messages have been reached to the broker and the broker is good to go, etc. So in systems like this, just make sure you are, you know, you fail fast. Okay, so this is the last mention. This is not a really a principle on scaling systems, but this is something you see people talk about, NoSQL systems. What these systems traditionally try to solve is write scaling. Scaling of writes, especially in a high availability system, is really a hard problem to solve. So some of the most commonly used you know, stacks are Dynamo, which came out of Amazon, Cassandra came out of Facebook, Voldemort came out of LinkedIn, and React is the open source implementation of Dynamo. So these are systems, and also you have a couple of other document stores such as Couch and Mongo and others. They are, they are clubbed under the NoSQL system and they are clubbed under the key value pair systems. But systems like Dynamo, Cassandra, Voldemort, React, they have a different semantics. They have a different interpretations, different guarantees. Compared to Mongo and Couch. It's a subtle difference you have to understand. So storing something internally through key value is different from a distributed key value store. So Dynamo, Cassandra, Voldemort, React are more a distributed key value store systems through which you actually take on, write scaling. It's a subtle difference, so that's something you should not just classify everything under one NoSQL system. So where do they give you a lot of advantages? This is a traditional flow. You have your web tier, you have your app tiers, you have your database. Whatever principles we talked, I mean, we know how to scale the web tier. It's just, adding more HTTP server boxes, assuming you've optimized everything per request. Same thing on the app tier, right? So it's like you're running an optimized performance per request. Then all you have to do is to add more nodes to it. But then the difficulty comes in when you're trying to scale your database, right? So, so some of these systems, especially NoSQL systems, help you to do read scaling. Write scaling. That's where Voldemort, Cassandra, or Dynamo comes in. So the last thing I want to talk about is testing and monitoring. So you have to, when you're building scale, when you're building high throughput systems, this is something that you have to do. So you have to replicate live use cases. You have to ping your systems with live amount of data, live traffic data, if possible. Take a percentage of traffic and see how your systems react. We have something called load and performance testing, where we figure out what is the difference between this release versus previous release, where how is the SLA doing for this particular call from this release to previous release, and you start digging deep into the low level calls and figure out you are good within your SLA. I mean, it's tricky to do it for all use cases that you do it on live, but at least you should be able to do it for the most common use cases. And another paradigm that you have to do is you measure everything. So you try to measure everything. So at least you log everything that you can, and then discard logging data. Right? So this space at some level is cheap, so you can afford to write. That doesn't mean you retain all those data for a long time, but you can keep partitioning them and then remove the partitions that are not needed. But where it's very interesting is we have run into this on production as well. So when you're calling once service A invokes service B, the SLA is published SLA is 50 millisecond. Service A invokes B, it gets a response back at 100 millisecond. Service B internally is monitoring its own request and response. So it says, I got this request from service A this time, and then I gave a response back at this time. So my SLA is actually 40 millisecond. I've done an improved performance. But then why is service A, it's it's seeing 100 millisecond compared to 40 millisecond, and it's probably because something that you have in your data center, some network delay, or the way that the network architecture is set up, something is wrong, right? So we were able to figure out some of these things. But what is critical is you have to do all this. Whenever possible, you try to do as much as you can. Just because you measure everything doesn't mean you have to monitor everything. What you monitor is what are some of your core needs. I mean, you try to monitor as much as you can, but then you are spread thin. So you try to measure as much as you can, but then monitor based on based on your needs. So not all services, like I said, not all data is equal. Similarly, not all services are equal. So to us, if the payment system goes down, it's extremely critical. If the settlement system goes down, it is critical, but not as critical as the pay system. So you have to have monitoring in place to figure out which systems are running and how good they are running, how is their SLAs, and publish their SLAs, not just the average, but the 95 percentile. and see where you are. These are some of the references. So as I said, none of this is really new. Everything is probably being talked about. You probably have read it someplace, or you have been involved in building systems that are doing this today. So a classic is Life Beyond Distributed Transaction by Pat Hedlund. Yeah, so other one is Eventually Consistent by Vogel. Classic a paper on eventual consistency. And then a couple of other references on building scalable internet architecture. And we have one there, Andy Sharpen. He was with the 5 years back. He talks about some of these principles as well. That's it. So thanks a lot. I'll try to take questions now. I'm not sure how it works, but I'll try to take it.
Thank you so much
Okay,
for this session.
first question is, what is SLA? Yeah, okay. So the first question is, what is the meaning of SLA? SLA is, it's a service level agreement. So if you're building services and if somebody is calling you, calling your service, you publish certain amount of SLAs around it. So you say, I'll get back to you within 100 milliseconds or 200 milliseconds. Whatever you publish is what people hold you to it, because they build systems based on that assumption. Other question is, what is the difference between synchronous scaling and asynchronous scaling? You cannot scale. When you're trying to scale, let me rephrase it, right? So what we talked about asynchronous scaling is a paradigm that you try to scale through asynchronous messages. It's very difficult to do synchronized scaling just because, if your systems or workflow involve hundreds of components, 300, 400 services, and you're forced to invoke half of them, your user experience is just not going to work. Even if you parallelize it, then that means you're not scaling very well. So yeah, so I hope that answers your question. So you try to scale through asynchronous messages. Scaling principles based same for both traditional web apps and mobile apps. Okay, the question is, scaling principles same for both traditional web apps and mobile apps? From a backend perspective, yes. So, like if you're building, if you're building an e-commerce site and you are building front-end clients that are web or mobile, it doesn't matter, right? So it's like people are going to invoke your services. The web is nothing but a glorified big screen for your tablets, right? So yeah, the principles are the same from a backend perspective. But whereas on a front-end perspective, it's a little bit different, right? So if you're going through, so I'm not going to get there. So it's a one separate topic on its own, depending on which platform you're in, etc. Android, iOS, or whatever. So scaling principles from a backend perspective are the same. So you should not actually see a difference between the web and mobile app. Okay, other questions. What is the meaning of not all data is equal? Please explain with examples. So I hope I gave you the example. So when I say all data is not equal, so as I said, a transaction, if you're in a transactional flow, the user profile data is not that critical to you. I mean, to you, the transactional data is a lot more important. Who's the buyer, who's the seller, etc. You're not interested in whether the buyer, recently bought something else, right? So when you're going through a transactional flow, that data is not critical. But then when you're going through a recommendation engine, that data is very critical. But then the transactional data need not be that critical. So when you're going through a recommendation engine for the particular user, this guy has brought a lot of baby-related items. So this probably is having a baby or is going to have a baby. So you try to give them a message saying, okay, we have some coupon or something for this type of product. So for those type of systems, uh, the seller is not that critical. Maybe the buyer profile data is. Well, the use of distributed cache aid in scaling. So that's a very good question. So see, so applications try to do it in a different way. So let me rephrase my answer to that. So most of the applications will have something called what we call app stickiness, right? So when you go through a checkout experience, most of the time they will try to. So if you go through one particular data center, they will try to read out the request, what we call app stickiness, to the same data center, right? So in a sense, if you are able to do any kind of caching within that kind of data center, any kind of caching within that particular data center, yeah. But then if you, for whatever reason, you route the user to a completely different data center, it's it's not going to be a great experience. But you try to avoid that use case. So it's probably you try to build an app stickiness in some other fashion so that that doesn't happen, because maintaining distributed cache is expensive. Okay, so any other question? What's the best method for processing messages from a queue? A reader which read and pulled messages to a processing or processing machine filling machines as per capacity. So the question is, what's the best method for processing queues from messages from a queue? So a reader which can read and pull messages to processor using load balancer, or processing machine pulling messages as per their capacity. It's both. It also, as I said, it depends on what you're going through, right? So I mean, if you have a good load balancer, it probably knows which machine are in what capacity. So in that way, you probably do it. But then most of the time, it's like you are trying to pull messages, and then depending on your capacity, you process it. So it is both ways. There's nothing like one good way to do it. But what we have seen in the past is certain protocols, queuing protocols, the way they interact with load balancers can be tricky. So it depends on that also. It's not just a high level answer. It is a low level answer. So you have to figure out what type of load balancers you are using and how your queuing protocols interact with that load balancer. Here's another question which I don't understand. So where is parameterizing scaling? Where is parameterizing scaling? So I don't understand that question. So it's from Shiva. So if you can repost that question, I'll try to answer it. Another question, next question is general when you should start focus on scaling, when app hits 100K request or 200K request and so on, or when your system actually gets slowed down. I think so. You should. There are certain principles like what I said, like partition by function, that you should do no matter what. So you try to at least build your code your code base such that it's a lot easy for you to, at least the code is modular, although it could be monolithic. But then Yeah, so obviously you may not have enough money when you're just going through 100K requests, 200K requests. If you have if you really see a need to do it, you do it. There are two answers to this. So one is what we call the Ben and Jerry model, where you do it when there is a need for you to do it. So if you really see a system slowdown, you do it. Or the other one is what they call the Amazon, Google, eBay model, where you do everything big, because if you are adding, because even anything small is significant. So if you're doing like any feature that's on Facebook level, uh, like 1% of user is probably millions. So in those cases, when your traffic by nature is high, you by default you have to do it. But when you are working in a small org, or it's a small app space, to begin with you don't have to do it, but you definitely have to focus on certain principles such as partition by function, etc. Those things will help you out in the long run. The question is when to make and how much to make a system process asynchronous. Is there a rule? There is no rule, but if you can make as much as you can asynchronous, it's better because your system remains kind of trim. It's in that sense you can your SLAs are a lot faster. Your response times are a lot faster. But having said that, it comes, as I said, asynchronous scaling is you have to make sure you're really doing what you're doing. So because you are firing a lot of messages at a given point of time, depending on what protocol you're using. I mean, if you have a queue that is a database-driven queue, a file-based persistent queue, you probably are okay. But then if you're taking something like AMQP and then trying to customize it for your environment, you have to be careful. You have to know what you're doing. But yeah, if you can do, there is no real rule, but if you can do as much as you can asynchronously, it's good. With the caveat being understanding how your systems work. And for some of these, there is no real, you just have to go through production pain to figure out, this has to be done asynchronously or this can be done asynchronously. So the question is, how do you define SLA when there is no performance metric defined for a particular system? Yeah, to begin with, when you're just launching your app or something, it's everything is fast, right? So nobody really notices something perceptible. But then you have a critical mass of users, then you start seeing systems slowing down. You start seeing systems, it's anything. It's something that might come from the outside world, right? So like users are saying, they're complaining, saying it's taking more time, or you're seeing a lot of drop-offs from your application because them being slow, or just as you add more and more data to your system, it's just slowing down and it's giving a bad experience to everyone. So at that point, maybe you haven't defined the SLA, but sometimes it might be given from an outside world. But sometimes if you're trying to build a system and you want to if you're trying to build a service and you want to introduce it to an existing system, then it might be driven by the constraints of the existing system. But if there is no performance metrics to begin with, whatever you do to begin, as long as if there is, you will hear it from your customers. Let me put it that way. Next question, does using more threads and request parsing against scaling principles? So as I said, that's you probably have to use threads, right? You cannot walk away from it. So if you get a request and then you are calling multiple services or invoking multiple services, you probably have to do it in a parallel fashion. So so that you maintain your SLA to your clients, right? So you cannot walk away from threads. But having said that, you shouldn't be like spinning threads like crazy. Uh, it's because, I mean, you spin threads for a reason, right? So, and then if you're taking too much socket or so much CPU with it, that means somebody else is not, you are disturbing the next request. So there's no real formula to some of these. The way they constantly say in the operations world is they monitor the CPU utilization, and the reason why they monitor those things is just because if you have a deployment on a given box that is taking on multiple services and your CPU utilization is greater than say 60% or something, that means it's somebody is doing something that's not right. And the reason is, if they're trying to do some load balancing, some services are down, and they want this particular box to take more, and you are spinning more threads, and in essence, you are consuming network and I/O. I'm sorry, you are consuming network and CPU. Then you're slowing down others. So as I said, you need threads, but there is a law of diminishing return, and you just have to figure out for your systems where they are. Next question, even if applications is scaled optimally, there could be a network configuration slowing down. Yeah, so anything is possible, right? So yeah, your network could go away, right? So I mean, your network, no matter how much whenever people do data center designs, they do have network redundancy, etc. But mistakes do happen, or they didn't think through something, or something entirely went down. It is possible to have network-based failures, and especially when you're talking to, like, for example, one data center versus another data center that's completely across somewhere else. Yeah, so you will have a lot of network latency, a lot of network problems. Yes, it's a given. So you try to build it, you try to figure it out. So I think that's one of the examples that I just mentioned was when you're measuring some of these things, you actually figure out there is something wrong with the network, and you might have to live with it, right? So you might have to live with it, and then you have to call your operations folks, and they'll try to fix it or try to correct it. So yes, so you're right. I mean, the only thing you can do is you can make your application robust as much as you can, and figure out that something is wrong, and then inform for folks to take corrective action. What is the right environment to test scalability, availability, dev, QA, or separate environment? See, like a separate environment is just for scaling is it's better at some level, because I'm sorry. At some level, it's better because your QA is probably testing functional code, and functional code, feature code, regression, etc. Right? So they are not probably, as a programmer, you're testing your unit test, etc. Right? So, but there is no, like, you don't focus on what happens if this particular operation is taking X number of things, or if this particular operation, if this has a dependency on this service, and if this service goes down, how am I reacting, etc. Right? So a separate environment would be ideal from that perspective, because traditionally when you do go through any kind of even through agile process, right, when you're going through your coding cycle, your testing cycle, it tends to be more focused on the functional requirements, right? So scalability by nature is not a functional requirement. So I mean, you can do a few things on the dev and QA environment, but a separate environment would be ideal. Is there any white paper sheet that explains different scaling techniques for web tier, app tier, and DB Yes. I have listed some of them as references. So one is Life Beyond Distributed Transactions by Pat Hedlund, Eventual Consistency by Vogel. It's a classic. And then Dynamo is also a paper that came out of Amazon. Cassandra paper came out of Facebook. So there are a lot of these things that talk about DB tier scaling, app tier scaling, etc. So yeah, so I'll try to send a note or something where you can get this. It should be out there, so it's common. Next question is from a perspective of testing. I understand that scalability is part of non-functional requirement and performance is a component of scalability. So what do you think? What type of testing completely validates scalability in SLA? Is it audit plus testing, or what do you think? So whatever, anything that can mimic your live traffic is probably the best way to test it. So auditing, when you're saying audit, I assume like you push your service to live and then you figure, you try to see what your SLAs are, and if they're very bad, you try to optimize from then on. But if you can take some amount of traffic, of live traffic, or invoke with live traffic, or if you're able to mimic your live systems, whatever way, in a test environment, or sometimes you believe it's difficult, you just have to deploy something. If you have a beta environment or some way for you to route some live traffic into your system, see how long it takes, to measure your SLAs. Can you use MongoDB for distributed transactions? If no, can you be more specific? So, okay, so you should try to avoid any kind, trying to do any kind of distributed transaction. MongoDB is, what I'm trying to say is it's a different, it's a document store. It's the constraints of that system is a little bit different from from the semantics of a distributed transaction. So can you do distributed transactions with Oracle? Yeah, but then you probably run something with two-phase command, some kind of quorum protocol, right? So whenever you go through any kind of distributed transaction, your system will slow down, irrespective of whatever it is. But when you're trying to do read scaling, my recommendation would be you should read about Cassandra or Dynamo or something along those lines. That might better fit your need if your problem is right scaling. Next question is, does it make sense to go through hybrid cloud implementation just for scaling, a burst of cloud when load demand? So yeah, that'll be ideal, right? So I think that's kind of what a classic example is. When you're going through transaction systems where people are doing a lot of transactions through the daytime, but then your settlement systems kind of kick in during the night. So if you're able to have a fine balance where you have a set of machines, but then they're taking transactionals, they're elastic during the day for transaction, and then during night they're elastic for settlement. Things like that. That'll be ideal. So that makes complete sense. So or like if you are selling something that like a sweet, and people tend to buy more sweet during Diwali, then you probably would like to go onto a cloud provider just for selling sweets during Diwali time, and then be elastic during that festival season, and then come back down. Right? So yeah, so that'll be the ideal way. Any open source tools for doing LNP? I don't know. I have to check and get back to you on that. Any particular variant of NoSQL DB you would suggest? As I said, I don't have any recommendation. It's up to when you're going through a NoSQL DB system. It's kind of a hot topic right now. So, but you have to pick and choose. So you have to pick. I mean, different things come with different. It's a product, so each product has its own pros and cons. So if you pick Cassandra versus Dynamo versus React, you have to, or Voldemort, you have to understand what is the guarantees the system is providing, and then understand that, and then take it up. Scalability in QC environment. So yeah, yes and no. I mean, it'll be great to do it, but it depends. So it's because your test systems are not as I mean, as they're probably. But there are tools. So for example, going back even to the previous question, I think Netflix has a tool called Chaos Monkey or something. I don't know if it's open source yet, where you can introduce chaos into your system. So if you have a system that does, depending on 200, 300 services, you intentionally introduce a chaos, the chaos monkey, which is nothing but a program to bring down some of these services, and then figure out how good your service is actually responding when some of these services go down. So yeah, there are tools for that. So I think you can probably search for chaos monkey from Netflix, I think. Can you explain which is a better option for a scalable model, NoSQL or MySQL? So it depends on what you're looking for, right? So MySQL is a relational database, so it has the constraints of, it gives you the guarantees of ACID, but then you can build some of the abstractions that we talked about, and then scale your systems using MySQL. As I said, you have to. There's a subtle difference between when they say NoSQL. The NoSQL movement is, I mean, it has two branches to it. Some of them, the Cassandras of the world, the Mongo, the Reacts of the world, come under a different guarantee system compared to the document stores such as, Couch and Mongo. So there is nothing like, a silver bullet. So you just have to look at what you think is right for your solution. Most of the time, your MySQL will work. NoSQL, you really have to think. I mean, if you are such a system like Facebook or Amazon, then yeah, it makes sense for you, especially on certain use cases like the cart use case in Amazon, cart use case in eBay, when when you want your system to be highly available for rights. Right, so that's when you prefer something like Dynamo or Cassandra. Well, tuning of VM improves scaling definitely. So yes, so your virtual machines have to be tuned up. So this is irrespective, right? So this is a good practice. This goes back to another question. Somebody was asking, should I scale at 100K or 200K, or is there a number? So these practices, like fine tuning your VM, is it's something you should do no matter what, and it will definitely help you scaling. I mean, it will improve your per request abilities. In a sense, in that way, you are improving your scaling. It's more cost effective as well. Okay, so I think that's it, the number of questions.
Well, yeah, those were the only questions we had for the session, Balaji. Thank you so much for answering them. I hope our attendees got answers to their queries. I'm really thankful to you for conducting this webinar. It was a great session.
Thank you.
I would also like to thank all our participants for the support in making this webinar a success. The recording of this session would be available on techgig.com by evening. Thank you all. Have a great day.